All right, here we have a problem that involves a refrigerator. And I like this one because it actually talks about the running of the refrigerator, the work being done, and then the cost of having to run something because, as you know, we don't get our electricity for free. So let's start working through this one. So the first question here asks us, what's the best coefficient of performance for a refrigerator that cools an environment of negative 30 degrees C and exhausts its heat at 45 degrees C? Okay, so let's look at this. Now, what clues me in here is this word here, best. What is the best coefficient of performance? So when you start seeing something like that, like maximum or theoretical maximum, that's when you should start thinking about Carnot. And if the problem gives you temperatures, right, instead of energy there, then you know that like, okay, I think I'm supposed to be finding Carnot here. And that's something that you're going to want to pay attention to in the wording of problems when you're trying to figure out when do I use Carnot and um, when do I just use the regular equations there. So I know that in order to use the Carnot equations, I need to be working in kelvins, right? Because negative temperatures wouldn't make any sense if you look at those equations, if you really kind of stop and think about that. I need to move to kelvins. So my T cold here is given as negative 30 degrees Celsius, which is 243 kelvins. My hot temperature is given as 45 degrees Celsius. And remember, this is like, say, if you were to put your hand on near where the refrigerator exhaust is, it feels pretty warm, right? That would be that temperature that they're talking about there. And in kelvins, that is 318. Okay, so that allows us to, it's a pretty simple calculation then to find the coefficient of performance. So we're talking about the Carnot coefficient of performance then, right? So the coefficient of performance, and I would put a little sub C down there for Carnot. That's going to every time be equal to the cold temperature over TH minus TC. There's a different ways of writing that, but it's essentially going to give you a ratio every time. So that'll just give me the 243 over kelvins, 318 kelvins minus 243 kelvins, which gives me 3.24. So that is my coefficient of performance, best coefficient of performance. So if you're asking yourself like what's the point of Carnot, why do we even use that if we can't ever get to that? And the reason that we use Carnot is because it allows us a really quick and easy way, given a temperature differential, to find what is the theoretical maximum performance of something, right? And you know you're not going to get to that theoretical maximum, but if that theoretical maximum is like way over and above, if you're going to be happy to like get to half of that efficiency or half of that performance, then you probably have a shot of building that system and making the system okay. If you know that that whatever you get as a performance or efficiency using Carnot is really what you would need to have to make the system worth building, then you know it's not feasible to build it. So it's a good way to sort of get a feeling for the system overall. Part B, how much work must be done in order to remove 100 kilojoules from the cold environment? Okay. So I don't know, you can imagine yourself putting some really hot food in there. And of course, it's going to take work, right? To remove that from the cold environment of your refrigerator and bring everything back down to whatever the temperature inside there needs to be. So um, the heat removed, then what we're looking at here for, I guess this is more like a freezer, looking at these temperatures here. So you're putting something warm right into the freezer, and then the freezer compartment needs to be cooled down again. So the heat removed from the cold environment, right? So I'm going to say here, heat transfer from the cold environment, which is what we're talking about here. That is QC. So in this particular situation, that's QC. QC is coming, and what the equation looks like, of course, your first law equation, it always looks like this, is QC plus work is equal to QH. So a way you can think about this in the freezer or refrigerator situation is QC is the heat transfer from the cold compartment. You need to keep doing that or else the cold compartment is going to warm up, right? So that's a fundamental part of running the refrigerator or freezer. And the work is the work that has to come in from the wall, right? The electrical work that needs to come in to make this happen, since the transfer of heat from cold to hot is not spontaneous and takes work to do in our universe. So coefficient of performance, we have that, right? The Carnot coefficient of performance, we could say, is equal to QC over work. QC is what we want to get out of the refrigerator. Remember, work is what we have to put in. So we could say that work is equal to QC, over the coefficient of performance here, where the coefficient of performance is defined. We already defined that in part A. All right, cool. Now we can sub in our values here. What is the work that has to be done? The work, it's 100 kilojoules, right? So that's going to be 1 times 10 to the 5 joules in scientific notation, divided by 3.24, and that gives me 3.09 times 10 to the 4 joules. That's what's being asked for in this problem, in this part. Okay, so notice that this isn't watts, right? This is joules. This was like to remove a particular chunk, right? To remove a particular chunk. We're not even talking about how long it would take to do that. So part C, though, does ask us, what is the cost of doing it? If doing this work costs 10 cents per kilowatt hour, right? So if you don't know how much electricity costs in where you live, that's something interesting probably to look up. And it varies a lot throughout the world and even throughout the United States, depending on where you are. It's very regional, depending on what the sources of electricity are in a particular region. So I like to put this problem in here because what I've noticed over the years is that students have heard of this kilowatt hour, and most students have electricity, but have never really thought about or spent time on what's going on there. So let's look at it real quick. So 1 kilowatt hour, kilowatt is 1,000 watts, right? Equals 1,000 watts times an hour. Yeah. That's what's a watt? Remember, that's a joule per second, 1,000 joules per second times 1 hour. Now you see what I'm probably going to do here. 1,000 joules per second times 3,600 seconds, right, is equal to 3.6 times 10 to the 6 joules. So 1 kilowatt hour we can write in terms of joules. That is a unit of energy. Sometimes people will see, all they'll hear in there is the watts and think that that's, when they see kilowatt hour, they think it's power, but it's not, because it's a kilowatt multiplied by a time unit. Yeah. So kilowatt hour is energy, not power. Again, that makes sense if you think that that's what you pay for, right? You don't pay for the rate at which you're using the electricity or the energy. You pay for the energy that you're using. So this is much more, it's much easier for most people to understand when it comes to water. Like they use a certain amount of gallons or something, or acre feet. However, it's usually expressed in terms of volume over whatever their billing period is, and that's what they pay for. They pay for the amount of water that they use. So similarly with energy, you pay for the amount of energy that you use. For people that use a lot of energy, like industrial applications and stuff, it's actually not the same cost all around the clock. You can buy cheaper electricity if you buy it off hours at certain times because of how the power plants work. Okay, that's a different conversation. Let's move on. So this question is asking us, what is the cost of doing the work if it's 10 cents per kilowatt hour? All right, so the cost, that's what we're trying to figure out here, is equal to whatever the work is that I'm doing, right? Which is going to cost 10 cents per every 3.6 times 10 to the 6 joules. Now I'm putting this all in joules because work is, of course, going to be in joules. And we defined work in part B, right? So we defined our work as 3.09 times 10 to the, times 10 to the 4 joules. If I multiply that by 10 cents per kilowatt hour, which is 3.6 times 10 to the 6 joules, what I get is 0.086 cents. Okay, so not much. Now, part D asks us for the heat that's dumped into the warm environment. So say this is just like you put something warm, remember the application here to think about, make it concrete. Say you put something warm in the freezer, which people tell you not to do, but you're like, oh, I've got to do this because I'm going to leave the house or whatever. So you put it in there, and now we've established how much it's going to cost to have that heat transferred out from the cold environment. And part D asks us, when we do this, how much heat gets dumped into the warm environment? And we know it's going to be more than just the 100 kilojoules, right? Because we remember, one of the things that we remember, I'm going to draw this out again in color, is when we look at our diagram, here's the hot reservoir, which is the exterior of the refrigerator, right? So say the kitchen, the cold reservoir, which is the cold compartment. And what we're doing in the case of refrigerator or freezer is we're having heat transfer in the opposite of the spontaneous direction, right? From cold to hot. In order to make that happen in the opposite direction, we need to add work to the situation. So what this means here is that the QH, which is the exhaust, right? This is the exhaust in this particular context, is not just going to equal the QC, which is like the heat transferred out of the lasagna or whatever. It's also is going to be the QC plus whatever work it took to make that happen. So that's what we're being asked for in this next part. And I'm running out of room, so I'm going to switch pages here. So part D, we want to find what is dumped into the heat transfer into the warm environment, and that, as we just saw, is equal to QH for this application. QH by first law is equal to QC plus work, and QC and work I have both defined there in part B. So all I need to do really is sub in those values, and QC is given there as 1 times 10 to the 5 joules, and work we found was 3.09 times 10 to the 4 joules. So that gives me, for my QH, 1.31 times 10 to the 5 joules.